Idea of how phasors and sine waves are related. Now let's put phasor diagrams to their real usefulness by analyzing some simple circuits.
Notice that this circuit has two AC sources. Voltage A is 3 volts and voltage B is 4 volts. It's stated that A leads B by 90 degrees. Notice the resistor connected in series across the two AC sources. Let's determine the peak value of the resultant voltage wave, which in a series circuit is identical to the total circuit voltage. There are two methods that can be used, a graphic method and a less time-consuming mathematical method.
Let's look first at the graphic method.
Using the schematic information, the two voltages are drawn. Sine wave A, which peaks at 3 volts, leads sine wave B, which peaks at 4 volts, by 90 degrees. To find the peak of the resultant wave, values along the two sine waves are added. Plot these along the horizontal axis, and the resultant sine wave will form when they are connected. Bear in mind that values are approximate because the waves are hand-drawn. Start at 0 degrees. A is at 3 volts and B is at 0 volts. 3 plus 0 gives an instantaneous value for the resultant sine wave of 3 volts at 0 degrees. Moving along the horizontal to 30 degrees, A has an instantaneous value of 2.59 volts, while B at this point is 2 volts. 2.59 plus 2 yields a resultant value of 4.59 at the 30-degree point along the horizontal axis. Now connect these 2 points to form a segment of the resultant sine wave. Continuing along the horizontal axis, by very careful measurement, you find that at 55 degrees, the value of A is 1.73 volts, and the value of B is approximately 3.27 volts. Adding these two values together yields 5 volts for the resultant sine wave. Extend the resultant waveform to include this point. Now move further along the horizontal axis to 90 degrees. Here, A is at 0 volts and B is at 4 volts. When added, these yield a 4-volt instantaneous value for the resultant sine wave. At this point, you can see that the resultant wave is peaking at 5 volts. If more points were plotted, the wave could be fully drawn by connecting the dots.
You can begin to see that the graphic method is time-consuming and requires a great deal of accuracy. Fortunately, there is another method which is much more efficient for finding the peak value of the resultant wave, the mathematical method. Before looking at it, let's review some simple principles of geometry upon which it is based.
A right triangle is one that contains a 90-degree angle. The two sides that form the right angle are called legs. The third side, which is always opposite to the right angle, is called the hypotenuse. When the length of the two legs is known, a geometric rule known as the Pythagorean theorem can be used to find the length of the hypotenuse. This theorem states that in any right triangle, the hypotenuse, designated with a lowercase h, is equal to the square root of the sum of the squares of the two legs of the triangle, labeled A and B. Here's the mathematical formula for the Pythagorean theorem. H equals the square root of a squared plus b squared.
Becoming familiar with the Pythagorean theorem will help you to master the second method for finding the peak value of the resultant wave. This method combines geometric principles with phasor diagrams. Let's see how.
Remember, it was stated that the two voltage sources are 90 degrees out of phase. Let's draw a phasor diagram with voltage A at 3 volts and voltage B at 4 volts. You've already seen the two phasors that are 90 degrees out of phase form a right angle. The resultant phasor, which represents the total voltage, can be determined using the Pythagorean theorem. This is true because the resultant phasor corresponds to the length of the hypotenuse opposite the right angle formed by the two phasors. This can be clearly seen when a dotted line extension is added.
Let's rewrite the Pythagorean theorem to reflect voltage values. The resultant or total voltage, V sub t, equals the square root of V sub 1 squared plus V sub 2 squared. Substitute the values from the example circuit. The total voltage equals the square root of 3 squared plus 4 squared, or the square root of 9 plus 16, which equals the square root of 25 or 5 volts. 5 volts, then, is the length of the resultant phasor, which is also the peak of the voltage drop across the load resistor.
Using phasors and the Pythagorean theorem enables you to calculate the resultant voltage from any two voltages that are 90 degrees out of phase. Let's try another example.
Here are two sine waves that are 90 degrees out of phase. Notice that the leading wave, V1, peaks at 8 volts, while the other, V2, peaks at 6 volts. Let's construct the phasor diagram. V2 becomes the reference phasor because it starts at 0 degrees. An arrow 6 units long is drawn along the horizontal axis. V1, which is 8 volts, is drawn 8 units long at a 90-degree angle along the vertical axis upwards from the origin. The phasor diagram is now complete. What will the resultant phasor be? Once again, its length will correlate with the length of the hypotenuse, formed by a dotted line extension. Substitute the example values into the Pythagorean theorem to get V sub t equals the square root of 8 squared plus 6 squared. This is the same as the square root of 64 plus 36, or the square root of 100. This yields the resultant voltage of 10 volts. Here is the phasor diagram showing the relationship of the two original sine waves, 90 degrees out of phase, and the resultant phasor of 10 volts AC.
Stop the program and complete activity number 2. When finished, continue watching the program.